Hello. In this video, I will be talking about how the vector databases actually store the vectors on the disk. This topic is gonna be really interesting because it will take us back to some fundamental DSA topics as well as some fundamental traditional ML topics as well. So, before we jump into how vector databases store data, we need to understand what exactly is a vector. Okay, so whenever you send an input string to your large language model, it cannot interpret the exact text. So instead, you have to convert or transform the text tokens into dense vectors. Okay, these vectors are basically an array which is containing a lot of floats, and this information is really dense. Okay, and if you lay this flat on a disk, searching for a particular vector in this dense information is really difficult. What are the options that we have? If you store it in the disk, you start reading it sequentially, it's gonna take forever because at the worst, you will have to read n dense vectors, which is really expensive. So, to trade off the speed, we started uh, compromising on the search accuracy. So instead of going for the exact search, we start doing approximate search, which is based on the nearest neighbors. So this is how the vectors uh, embeddings are stored and how they are retrieved. It's based on the approximate nearest neighbors. So when you understand, when you hear the term nearest neighbors, it should take us back to the times in the traditional ML systems when we were learning about clustering, because that is exactly what the vector databases use. Okay, so look at this example. Imagine each of these dots represent a single vector. Now, when you transform the text token into an embedding, it basically goes into a higher dimensional space. And when you have enough vectors that are present in this space, they will start forming clusters. Okay, so in this image, you can see we have three clusters, and an interesting property of a cluster is that it can have a centroid. So we can say a centroid represents a subpart of the cluster. It is a representative of the cluster. Okay, and what is the algorithm that we have learned that determines the centroids? Which element should become a centroid? K means clustering. So a technique that I'm going to talk about is called IVF, which actually uses the same k-means clustering and the centroid logic to implement the vector database. Okay, so for this particular approach, inverted file index, it is IVF, and it has two major components in it. So one is the centroid index, and the another one is the posting lists. Okay, so we have a centroid index and then we have a posting list. So the centroid index basically stores a centroid, okay, a centroid. And what is the vector representation of the centroid? If the centroid is a token ADITYA, then what is the vector representation of this token? This mapping is stored in a hash map, okay, in the centroid index. And the other data structure that we use is the posting list, which basically has the key as the same centroid, okay, and the value is a long array, contiguous memory location that we have. So each of the element of this array is going to be one of the members of the cluster. Okay, so when you have this centroid C1 and then you have these three items that are sitting over here in this array, it basically represents this part. So C1 is the centroid, and these are the members of the cluster. Okay, so all the members of the cluster are mapped against the centroid in this data structure. Okay, so far is it clear? We have a hash map which stores the centroid and what is the value that it represents. And then you have the posting list, which again stores the centroid and what are all the members of this cluster. Perfect. So, how does this search actually occur? So, when you have an input token called ADITYA and you turn it into a high dimensional embedding, now you go and you look on the index, you do a lookup on the index. Okay, you look up on the centroid index and you find the centroid that is most closely associated with your input token. So let's say the input token is most closely associated with the centroid C2, which means there is a possibility that my token is actually a member of this centroid, the cluster that is represented by the centroid. So now I'm going to go and I'm going to expand the cluster, and then I'm going to look at who are all the neighbors of this centroid C2. So I go in this data structure and I see, okay, C2, I have n number of vectors that are sitting over here. And out of these elements, I'm going to see if the input token is actually a member of this cluster or not. Okay, so this is how your uh, nearest neighbor, approximate nearest neighbor algorithm works using the IVF. So it is very simple and straightforward to understand, but it has certain limitations. Okay, so let's understand what are the limitations. So the very first limitation is the boundary effect. Now, since you have multiple clusters, okay, so how will you decide where a particular point belongs to if the point sits on the intersection of two different clusters? Okay, imagine that you have these two clusters and we have a point that is sitting at the boundary of these two clusters. Okay, so how will you decide that if X belongs to the cluster represented by C1 or X belongs to the cluster represented by C3? Now that is a challenge. So one way to address this limitation is to use the nprobe parameter. So databases like Milvus will have a parameter called nprobe, and that basically tells us whenever you are doing a lookup, don't just look up in one cluster, also look up in some neighboring cluster. So if this element is sitting over here, then I'm not just gonna find its neighboring elements in the cluster represented by C1, but I will also check the neighbors in the C3. Okay, but now be careful, because if you increase the n probe, then the amount of data that you're gonna scan is also increased. So that is where your performance will get a hit because of more number of clusters being explored. So that is the first limitation of your IVF. Second limitation is the data drift. So K-means clustering is quite static. The reason being, when you add more number of elements to your data set, the centroids tend to move. Okay, and the K-means clustering takes care of this by computing the centroid n number of times, and after, let's say, k attempts, if the centroid doesn't change or it keeps flipping between two or three specific values, in that case we are going to come to an end, and that is the natural end of the k-means clustering. So whenever data drift occurs, the centroids, they do not represent the entire cluster anymore, and that is a problem. The whole point of using the centroids was to find approximately what is the region where my token belongs. But if the centroid no longer represents the region, then the search is not gonna be good enough, right? So the data drift is another limitation that you have with the IVF. And the last limitation we have is the sizing of the inverted list. So you can see the posting list is actually an array. This part over here, this is an array, and an array needs contiguous memory blocks, right? The reason the array is a fixed sized data set is because we have reserved a specific amount of memory for this array to expand, beyond which we cannot. So if the amount of elements in your inverted lists are growing rapidly, then you cannot add another memory block and just expand your array over there. What you have to do instead is reserve a larger memory location, copy all the elements from the previous location to the new location, and then now you have enough room to add the new element. So this is the limitation around the inverted list sizing. That is, if you have a lot of data updates, in that case you will spend a lot of time in copying arrays. Okay, so your writes will be slower over here. So this is how the IVF works. Now let's move on to another interesting algorithm, that is the HNSW. HNSW stands for the hierarchical navigable small world. Okay, so what does that exactly mean? There are two important words over here. One is the hierarchical, the second one is the navigable, right? So that tells me there is a hierarchy in it, and the hierarchy is navigable, right? So I can explore in this particular hierarchy. So internally, this algorithm is implemented, or this strategy is implemented using a data structure called a skip list. Okay, so some people say it's an advanced version of a linked list. Some people say it's a graph. For all practical purposes, it's both. Okay, so it's a graph that has multiple levels to it, and at each level you have some nodes that are representative of all the nodes in the layer below it. Okay, so let's have a look at what the graph actually looks like. So at layer 1 you only have two nodes, but at the layer below it you have more number of nodes. Now again, this node over here is a representative of all the elements that sit under it. Similarly, this element over here is representative of all the elements that sit under it. Okay, so as you go from the top layer to the bottom layer, the density of the data increases rapidly. Okay, so at layer 3 you can see there is a lot more nodes as compared to the layer 2 and layer 1. And this is the true superpower of the skip list data structure. That is, let's suppose you're looking for a particular token in your entire data set, and you have already constructed the skip list for it. So you start exploring at the level 1 from left to right. And let's suppose you find out that the input vector is very similar to the node, this particular node at layer 1. So the next thing that you do is go to the next layer and start searching in the next layer for all the elements that are children of my node in the layer 1. Okay, and now you just expanded the search space to a certain degree. Again, let's say you found that your input token is more similar to this particular node over here. Then you're again gonna go and expand it. Likewise, you're gonna go n levels deep until you reach the last layer where each and every node or each and every vector sits. And this is the most densest layer of the entire data structure. And this is how you navigate the data structure, which is hierarchical in nature, which is where the names come from, the hierarchical navigable small world. So this sounds interesting, but what are the limitations of HNSW? So let's talk about that. So the very first limitation that we have is the RAM bottleneck. So HNSW is very much RAM hungry because whenever you build this graph, it must sit in the RAM so that you can actually traverse it. Okay, so doing that uh, eats up a lot of RAM, which will create a bottleneck if you don't have enough resources. The next limitation that we have is the construction latency. Now, the building this data structure in itself is more expensive. So for IVF, we said it uses the k-means clustering algorithm to build the index. Similarly, over here, building this data structure is also expensive. The reason being, every vector that uh, every time you add a new item to the index, you have to essentially travel the entire existing graph and find the neighbors, and then you run a heuristic to check if an edge belongs between these two nodes or not. So this is very expensive operation, and if you have millions of vectors, so building the index itself can take some time. And the last limitation for HNSW is the deletion mechanics. Since we have optimized this data structure for read, the trade-off is that writes are slow. Specifically, the deletion is slow. Now, why do I say that? Now, let's suppose I want to delete this particular node from my skip list. So, in that case, all the nodes that are children of this node, they should not get cut off from the rest of the graph. They should be adjusted somewhere else. Maybe it becomes part of this node or it becomes part of this node. So, this readjustment takes some cascading effect. Okay, so when you delete this node, you will have to readjust this node, and because of that, the node over here may no longer be representative of the three elements because it was representing the two elements over here. So in this fashion, you will have to traverse all the way up, adjusting the new changes, and that is where the deletion becomes much slower. So possible solution for this is, instead of doing hard deletion in your graph, some databases prefer doing soft deletes on the system. So this was about how vector databases actually store the information uh, inside of them, and I'll see you in the next video.